Hello, thank you very much for attending this presentation. My name is Pedro Jimenez. I'm a PhD student at Universidad Carlos III de Madrid, and I will now present you some numerical results of simulations for the electromagnetic fields in the far plume of a Helicon Plasma Thruster. Let's first now introduce very briefly the devices we are working with and modeling and experimenting in the lab. The Helicon Thruster is an example of electrode-less device. This new technology promises some advantages compared to conventional electric propulsion, such as longer lifetimes, high throttability, and high thrust density. The principle of operation is the ionization of a neutral gas and the plasma heating by the electromagnetic power coming from a helical antenna, and then the acceleration of the charged particles in a magnetic topology that can be created either by solenoids or permanent magnets. At the Plasma Physics and Space Propulsion team, we work mainly with devices for small satellite propulsion, with powers ranging a couple of 100 watts and thrust in the range of millinewtons. There are still several challenges before entering into service. The main one is increasing the overall efficiency of the devices, and for that we want to understand better the physics. An important part of this physics is the radio frequency coupling, or the wave propagation and absorption inside the plasma, and this work will focus on that. So the team has now been working for a long time on the wave propagation and absorption problem for electrode-less thrusters. And besides some 1D simulations and preliminary studies, we achieved full wave simulations for HPTs in a 2D domain. Last year we were able to couple the plasma transport and plasma wave interaction for a self-consistent solution. So for the plasma dynamics and transport, we are using a Hyphen tool, which is a multi-thruster hybrid peak and fluid code. And for the plasma wave interaction, we have several modules. For HPTs, we are using a finite difference method. And for the ECR thruster, we also have published paper using a finite element method. Let me very briefly explain to you the process to achieve the coupled simulations, because this is a very important part of our research. Firstly, we give an initial guess for the plasma profiles, mainly the density and temperature. Then we call the wave module and compute the power deposition maps. We use this power distribution to advance the plasma dynamics in time. After some time steps, when the plasma profiles have changed significantly, we will compute the power deposition, calling again the wave module. This process is repeated until a stationary discharge of the thruster is achieved. We have some efficiency and thrust figures. And so we come to the objectives of this work, which are mainly to study the electromagnetic power deposition and the wave propagation in regions that were never explored before. So you can see here that we're using a pretty small domain due to some limitations in the numerical performance of our codes, both for the wave simulations and for the coupled simulations. So now we have extended this domain to include the far plume and also some regions of the vacuum chamber. We have also included some metallic parts, components, that are modeled as internal boundaries in our finite difference code. We are going to focus here on the electromagnetic solutions, so these are not coupled simulations. But anyways, we will show that they are a good approximation of the power deposition, and they provide a good insight into the physics of the discharge in the thruster. The plasma profiles, which are the input to the wave simulation, come from the Hyphen coupled simulations in the small domain. We will use a different methodology to compute the density and temperature in the far plume, and we will give representative values in the rest of the vacuum chamber. Right now we have some numerical problems to extend the Hyphen domain downstream to the far plume, but nevertheless we can use another tool that we have in the team, which is called Imagno. This is a two-fluid collisionless code that integrates the solution along the characteristic lines. So that way we can know the plasma density and temperature at the plume, in the expansion, and we can use the plasma profiles, or hyphen, in the small domain, the magno profiles in the plume, and give representative values for the rest of the vacuum chamber. By the way, we will estimate electron and ion collisions both at the plume and vacuum chamber because we know they dominate in these regions. And we will use them in the wave module. For the transport, remember that the magno assumes that we have a collisionless expansion. Let's take a look now at the 2D model we are using for the HPT and the inputs to the electromagnetic simulation that we are going to carry out. Here we have the simulation set up. So first of all, remember that this is an axisymmetric simulation, and the axis of symmetry is located here at radius 0. You can see the large domain that we will use in the wave simulations, and the small domain that was used before for a couple simulations. In magenta you have the antenna. We have some black boxes corresponding to metallic parts, particularly this one is where the coils are located, and they create this magnetic topology. The color map shows the electron cyclotron frequency, which is proportional to the magnetic field strength. And you can see here absolute values of the magnetic field strength inside the tube. An interesting feature of this figure is that downstream in the plume and chamber, we are crossing the electron cyclotron resonance. This is going to have important consequences that we will see in the results for the wave propagation and absorption. Here we have some numbers for the operating regime that we are simulating. The antenna frequency is 30 MHz, which is typical of Helicon thrusters. The power is 350 watts. We have an applied magnetic field inside the tube of 1500 Gauss and a mass flow of 1 milligram per second. As long as we consider a cold plasma, the inputs we need for electromagnetic wave propagation simulation are the electron density that you can see here in this plot and the effective electron collision frequency. This collision frequency is output by hyphen in the small domain, considering different types of elastic and inelastic collisions. But for the plume and vacuum chamber, we will compute them assuming that we have electron-ion collisions. Due to the presence of some numerical noise, very short wavelengths, we decided to scale up a little bit the effective collision frequency. We hope that we will solve this problem in the future and we can have nominal collisionality simulations soon. Another degree of freedom that we have is the chamber background density. So this can be very different. For instance, in a space environment, we will expect a near vacuum here. But in our laboratory vacuum chamber, we will certainly have an overdense plasma. The plasma frequency is larger than the antenna excitation frequency. This will affect the power deposition and propagation, and we will see that in the results. So before continuing with the results, let's see very briefly our wave propagation model and the numerical implementation that we are using. Okay, very quickly, we start with Maxwell's equations, realizing that this current density term has to include both the antenna current and any plasma currents that we have. So if we go to the plasma dynamics, we can neglect any pressure term because we are using the cold plasma assumption. And in that way, we find a linear relation between the electric displacement field and the electric field. Here we are using this dielectric tensor, and the dependency with the plasma parameters can be seen inside this tensor. Here we have the plasma density modeled by the plasma frequency. We also have the cyclotron frequency that is dependent on the magnetic field and the effective electron frequency. We will rotate this tensor in space to account for the direction of the static magnetic field created by the coils. A convenient discretization is used for the circulation and flux integral terms in the system of equations. This is based on the well-known G method. The main difference with the vacuum G method is that we have to perform some interpolations between the electromagnetic fields in the different node positions to account for the presence of the plasma. The boundary conditions for the domain are perfect electric conductor walls in the lateral wall and top wall, and some continuity conditions for the axis depending on the mode number. Now I want to show you some simulation results varying the chamber background density. In these results, I am showing the electric field norm and the power deposition for the underdense case. This means that outside the thruster tube and plume, we have an underdense plasma. In this case, it is just vacuum, but we expect something similar in the in-space operation of the thruster, at least a very faint plasma. The first thing we can notice is that in the overdense region, where the density is high, the electromagnetic fields cannot propagate beyond the ECR surface. This was expected from the wave propagation theory in plasmas. On the other hand, in the underdense region, fields can propagate beyond the resonance. This means that we can have some free space losses. Of course, in the power deposition, we don't see any power deposited outside the bulk plasma. This is because we have vacuum and plasma currents cannot exist in this region. Inside the dense plasma, we see some wave patterns that seem to propagate perpendicular to the magnetic field lines. Those correspond to the surface or TG wave mode. And we also see some longer wave patterns that propagate parallel to the magnetic field lines that correspond to the Helicon mode. Both patterns are instances of the well-known Whistler wave that occurs in this overdense plasma region. We see that the maximum deposition is inside the tube, but the deposition in the plume is quite significant. It is also important to remark that in these simulations we have seen significant numerical noise in the transition between the underdense and the overdense plasma, and this is something to be concerned of. We want to improve this behavior by including more node density, higher node density in that transition line, but for that we are planning to use a finite element mode in the coming months. Okay, so this is a different study case in which we set the background chamber density to a value of 10 to the 14 particles per cubic meter. This value is representative of what we think could happen in our chamber in the laboratory. So the first observation that we can get from these results is that the strongest fields are located inside the lower density plasma here, but the maximum deposition is still inside the tube, which is desirable. We can also see that a kind of diffuse pattern of waves forms between the ECR resonance surface and the border of the dense plasma. So what we think is happening here is that the waves are reflected back and forth between this surface, the resonance, and the border of the dense plasma. The ECR resonance surface seems to be a really good confiner of all the electromagnetic power. Indeed, we don't have any significant deposition outside. This means that our boundary conditions are a good selection, in this case perfect electric conductors, because we are not going to have any reflection back. So it doesn't matter that the vacuum chamber walls are located a little bit away from this resonance surface, because this is not going to affect the results. It is important to remark as well that inside the ECR surface bubble, this region defined by the resonance, the only wave that can propagate is the Whistler wave. So both the diffuse pattern of stationary waves from here and the TG modes, and you can also see some Helicon modes here in the plume. Uh, all this propagation corresponds to the Whistler wave, and this is because we have an overdense plasma both in tube and plume and in the vacuum chamber. So we don't have different regimes of propagation. We neither have the underdense to overdense transition in this line. Numerically, this is really a good thing because we have a lot of problems with that transition, especially when the transition is not aligned with the mesh. So here at the divergent topology of the plume, we have a lot of problems in the underdense and overdense transition that I have shown you in the last study case. Here we see a comparison between the power deposition in the large domain simulation and in the small domain simulation in the tube and near plume. And what we see is that the normalized map is quite similar in both cases, so the solution is really local. It is not affected by the fact that we are including most part of the plume and vacuum chamber. On the other hand, if we integrate the total power, we see that the power in these regions is lower in the large domain simulation than in the small domain. This just means that some of the antenna power is being diverted and it is being used in the plume and in the vacuum chamber. Here we have a convergence map, convergence plot, and we see that with significantly high number of degrees of freedom, so these are expensive simulations already, we have good convergence. This figure shows the fraction of total power and the power delivered at the source for different azimuthal mode numbers. So remember that we are performing a Fourier series expansion in the azimuthal direction to account for the fact that the antenna current density is a 3D function, but we are working with 2D simulations. And what we see is that the mode m equal 1 is the most important. This has already been shown in several works for Helicon sources. But here there is another remarkable observation that the mode m equal to -1 is also relevant. So the ideal procedure would be to consider both modes. By the way, here you see that even mode numbers that do not contribute to the power deposition for helical antennas. So let's finish with some conclusions and propose future work. We've seen from the simulations that the background density has an important effect on the field propagation and the power absorption. We've also seen that the electron-cyclotron resonance seems to produce a very effective power confinement, and this is more remarkable even in the overdense case. The fraction of power deposited in the plume is in general not negligible, and this is going to change the behavior of the thruster. This is not necessarily bad, because this power deposited of the plume can be effective for the thrust generation, but it is important to consider it in the near future. We also see that the normalized power deposition inside the source seems to be quite local. It doesn't change by enlarging the domain, but the total fraction of power changes. So some power is diverted to other regions like the plume or vacuum chamber. As future work, we want to increase the numerical convergence of the results, and we prefer to do this not by increasing the number of degrees of freedom, because we already have a lot of degrees of freedom and solving the linear system is quite expensive. What we want to do is to increase the node density in critical regions in short wavelength regions. And for that, we need another method, not finite differences. We want to use the finite element code. And we are working already on that code. We have to include the azimuthal mode numbers, which is the new feature from our previous finite element tool. So thank you very much for attending and listening to me. And now I'll be glad to answer any question that you have.